Hello and welcome everyone to this week's webinar. I will say that I'm pretty happy to be a part of, continuing education and learning during this time. And having said that, I hope that everyone is doing relatively well, all things considered, and enjoying and appreciating that we're still able to provide, services and presentations like this as well. My name is Damien and I work with our manufacturer partners such as Amiad, and I will be in the background moderating this week's guest webinar. And I'll say quickly, I actually like the relativity and continuity that seems to have arisen from the last few months of guest webinars, because it can provide a bit more of a well-rounded learning experience across a number of different sources. This week we have Ron Krause of Amiad Water Systems on to talk about improving water quality by mechanical filtration. And Ron will explore what water quality means to an irrigation system and some important factors that play into keeping that water quality at a high level, such as water sources and more. But just to take a very short sidestep, if you're interested in specific types of water sources like rainwater, we actually just had a great two-part series that can be related to, in part, with today's webinar on rainwater harvesting for landscape irrigation, which can be found on our website via our resources and videos page. So that's what I meant just by relativity and continuity there. I like we're able to round out this kind of the first quarter or first half of the year with something like this. But yeah, before I hand over to Ron though, I want to remind everyone of a few housekeeping items. We absolutely encourage questions and interactions with us each session. So if you do have any questions throughout the webinar, please type them into the Q&A window, which can be accessed by clicking on the Q&A button on your screens. Some questions will be answered directly by myself or other panelists in the background. Otherwise, we will have a moment at the midpoint of the presentation where we can ask Ron some questions live, or we will have our time at the end to get Ron definitely some questions there as well. But from here, I will hand over to Ron to introduce himself and get us underway with today's presentation. Thank you, Ron.
Great, thank you, Damien. Appreciate it, and appreciate LandFX for allowing us to participate in this webinar and to share about mechanical filtration. As Damien said, I am Ron Krause, and I am with Amiad Water Systems. I'm a regional sales manager. I've been there for just under a year. I have an extensive background in landscape and have been in it pretty much most of my life. Amiad Water Systems has been around for quite a number of years, 50 years plus. They have about 700 employees and they are a worldwide company, and filtration is all we do. So we're going to get into the topics of filtration and go through a few items here that we'll talk a little bit about what filtration is and why we need it. But basic definition of filtration is the separation of solids from water, and it's particles larger than a certain size need to be removed in order to protect our irrigation systems. Some of the main causes of emitter clogging in the irrigation systems are living organisms, bacteria, viruses, and microalgae. Some suspended solids, algae is another one, silt and sands and clay. And then dissolved minerals such as salts, calcium. Those are a little harder to filter, but they can be filtered. We're going to focus a little bit more on the living organisms and the suspended solids in this presentation. So as we can see, some of the major effects of clogging without filtration. And I'm sure many of you have seen this and or have had issues of this in times past. Clogging of the system can have a severe effect on distribution uniformity. This term is used to define a system's efficiency and performance. For every 10% decrease in distribution uniformity, it's calculated as a 30% wasted water or loss of water. And with water being such a precious resource right now, it's not a good practice to have that kind of decrease in your uniformity. And since the industry is moving to lower application rate emission spray devices that require more filtration in order to protect them, such as some of the high efficiency nozzles and drip emitters that we see out there on the market today. Clogging can have the effect on system downtime for maintenance and repairs, driving up costs for maintenance. It creates a negative visual appearance for the property and maintenance contractor and designer, and loss of costly plant material, which none of us want. So the main defense against clogging is mechanical filtration. The filter element is trapping and removing suspended solids from water, not dissolved minerals such as calcium, as we mentioned earlier. So again, why? Well, we want to protect the emission devices from clogging or damage, because with the higher efficiency nozzles nowadays, generally it's harder to clean those and to reuse them. When they get clogged, they're not reusable. And so again, costs factor into that. And also to maintain uniform distribution of the water and fertilizers throughout the irrigation system. So in order to understand water or filtration, we need to understand a little bit about our water sources, some of the water sources that Damien mentioned earlier. Our first one we're going to talk about is municipal water, which many of us use. It's probably the most common. Potable or culinary is another term for it. The quality of this water is good, generally. It is in limited supplies and it's very expensive. However, filtration is still required on micro irrigation, such as drip and high efficiency nozzles, because again, the particle sizes that you might still see in that water will cause issue with your emission devices. Surface water is another popular one that's being used on golf courses and other larger communities sometimes when they have lakes or aquifers close by. This water quality is sometimes poor. It can be hard to access, but it's becoming more and more popular alternative available. You're going to have filtration needed, such for the sands, silts, and organics that you'll see in that water. Well water is quite popular as well, but it's also something that's not available at all properties. It's a good to average quality, so it still requires some filtration. Gray water, reused from discharge of property. It's not as common, but it is something that is being explored. It can be an expensive setup. It requires more specific filter than an off-the-shelf filter. You're going to see sands, silts, organics, hair, fiber, other things that are hard on your emission devices, so filtration is required. As Damien mentioned, rainwater, stormwater collection and reuse, that's something that's very popular nowadays. It's an expensive initial setup, and it's dependent upon rain, but it's also something that's very inexpensive and it has a great ROI. You're going to still need filtration for sands, silts, and organics that are part of that system as it collects into its cisterns. Recycled water. In California, that's another big one where we use effluent or non-potable water. The water quality is poor to average. Your initial setup is costly, but it's only if it's available. But it also has a filtration need. Sands, silts, and debris, and sometimes organics can cause issues. So we want to talk a little bit more in depth about the principle of water filtration. And in order to understand the principle of water filtration, we need to understand some of the terminology. The first term that we have come across is micron. And what is a micron? Micron is a 3D diameter size of particles. And a micron is defined as equal to 0.1 or 0.001 millimeter, a little more than 1/25 thousandths of an inch. Just in reference for you out there who don't think that way, I don't think that way. The human eye can only see 40 microns. So pretty small dimension. There is a standard for filtration size, and it's declared filtration size is micron. They are results of performance tests done by an official lab using Arizona dust or glass bowls. Filtration size will be considered if filter will restrain at least 85% of the particles of the declared filtration degree. So it's important to remember, it only has to be 85% efficiency in order and collect those particles in order to be declared to that degree. The test should be done by an independent lab that operates according to the ISO 17025 standard. IFTS, International Filter Testing Services, is the international reference for solid liquid separation. So this will give you a little bit more reference in terms of the sizing of a micron. On your left is a micron. So we go all the way from 0.0001 all the way up to 1,000 micron on this chart. A hair is anywhere from 20 micron all the way up to maybe 600 micron. Most of what we deal with in landscape is particle filtration that we would be running into in those ranges between 10 and 1,000 micron. This gives you a little bit more information in terms of what kind of elements that you would look at. Clay, algae, those items are going to fall into that 10 to 1,000 micron that we discussed earlier. So there are quite a few available technologies out there for filtration. We have 4 listed here. There's centrifugal separators, there's automatic screen filters, automatic disc filters, sand media filters. We're going to focus more of our efforts on automatic screen or screen filters in general, because those go all the way down to a 10 micron. This is a slide representing a 500 micron before and after filtration. Kind of like one of those Lysol commercials where you see 99.9%. Again, this is in reference to the IFTS standard is 85% is collected and protected. Give you a little bit more earthly real world scenarios here. These are non-filtered or insufficient filtration where the line has actually run through with dirt. Some of these actually are clogging the pipes, not just the emission devices. So it's important to remember that we have to be able to protect our emission devices, but also our flow, which helps to keep our increased uniformity higher. Okay, so micron versus mesh. Many of us here are familiar with mesh. Mesh was initially instituted in the garment industry because, and the reason why that term was used is because many of the filters were actually used fabric or garment industry or garment in order to filter water. So mesh of a screen is how many wires are there in 1 linear inch of screen. And again, it's a definition that was taken from the garment industry. Micron of a screen is 1/1000th of a millimeter, the actual dimension of the opening of the screen between the wires. So the actual area that allows whatever particle to flow through or to not flow through. So micron is usually more accurate because again, it doesn't take into consideration the, the size of the mesh. It only takes into consideration how many there are in 1 inch. Screen filtration degree terminology. There's nominal filtration, which is the degree in an actual linear dimension of the shortest straight line distance, length or width across an individual opening or pore of a filter medium. The absolute filtration degree is the length of the longest straight line distance across an individual opening or filter medium. As you can see, perforated has only an absolute measurement because it's circular. The wedge wire has both nominal and absolute. The weave wire has both nominal and absolute. Perforated is typically a 3,500 to 800 micron, so fairly large. Wedge wire is 800 to 500 micron, and woven wire is 500 to 50 micron, which is more in line of what we'll see in our industry. So filter area and filter effective area, two different terms here. Filter area is the square inch area of the filter. So if you were to take and lay out the filter and measure length times width, that is your filter area. Filter effective area is basically your micron, your dimension, your absolute dimension, or 3D allowance of what can go through that screen area or particle size. So within screen filters, there's 3 different styles of cleaning. There's manually, which is physically remove filter element, scrub and wash. Obviously time consuming. There's backflush, where you reverse the water flow through the filter, dislodging and washing out particulate. There's focused backflush, where you reverse water flow through nozzles, concentrating cleaning to less than 1 square inch, which increase suction force. So in comparing these levels of technology, we kind of go back to our water supplies and help determine what maybe the best solution is for water filtration. If your water quality is good, for example, municipal supply, it's probably okay to lean towards a manual filter that's a little easier. You don't have to clean it as often. It's going to manage itself just fine. If your water quality is good to average, better solution is maybe more of a semi-automatic, that you don't have to necessarily shut the system down and tear it apart to clean it, but you can have the ability to clean it and manage that system just fine. If your water quality is average to poor, it's probably best to go with a fully automatic system. So in consideration for sizing of a filter, there's 4 key parameters that we talk about. Flow rate, your gallons per minute, how much water you're pushing through that system at any given time. Your static and dynamic water pressure, this is your PSI. Your water source, it's like we talked about, average, good, poor, what kind of water are we using? And then your last question you want to ask is what are you protecting? If you're protecting some high efficiency nozzles or drip emitters that have a small orifice to allow water to come out, you're going to want to have a better system and a better filtration system.
So I suppose, yeah, this was a point where we're going to ask a couple of questions. Ron, we were just wondering, when it comes down to water quality as a whole, what does that actually mean to you, and Amiad, and why do you think that's important when it comes to landscape applications?
Well, so it kind of relates back to what you're designing, what kind of system you're putting in. If you're putting in high efficient nozzles or precision nozzles or drip emitters that have small orifice, you've got to consider what kind of water you're pushing through that system. And again, when we talk about water quality, we have to talk about the waters that are available to us and the costs that relate to that. So every time we go into a larger project, we may be considering how much we have to spend on water in order to make that project happen. And the way water resources are today, we want to take that into high consideration. So with those two terms coming together, we want to allow to protect our emission devices because those are a costly event. And as those get clogged and or as those have issues, our system's efficiency goes down. So if we're protecting drip emitters and we don't protect them properly on the front end with our water source, then we're going to have issues with our plant material, our landscape, and the aesthetic beauty of our landscapes.
Yeah, fair enough. That kind of plays into, I guess, a second part of, or another question. Are emission devices really the only place for clogging to occur in an irrigation system? Whether it be simple or a complex one, and what might the costs be involved? Whether they're monetary or labor or system costs involved in fixing such issues?
So that's a great question. It depends on the quality of water that you're bringing into the site. As I mentioned earlier, if you're bringing in a municipal water and you're running that through a system, it's probably not going to have the likelihood of clogging anything other than the small orifices of the emission device. The cost that's associated to fixing that and or to ensuring that your system is up to date or is highest efficient that it can be is relative to the cost of how much time it takes to maintain that and or to fix that and replace that. Like I mentioned earlier, the emission devices nowadays, they're so complex in some degree in how they emit the water that when they get clogged, instead of being able to blow through it or clean it out as what you would do in the old days, it's almost near impossible to clean those to be the same type of an efficient system that they were before when they were brand new. So nowadays, more times than not, you're replacing those systems or replacing those nozzles. And those nozzles are off the shelf at retail costs are $4 and $5 a piece, depending upon where you're at.
Okay, yeah, so the cost could be considerably high if you're
Yep,
working with a pretty complex part.
exactly.
Cool. I got another question. In one of the pictures previous, you presented zebra mussels.
Mm-hmm.
The question is there an actual way to remove zebra mussels by filters?
There are, that's a pretty complex question. And that one has got a lot to do with, we've actually dealt with that. We've put systems in place to manage zebra mussels. Removal of zebra mussels is not going to probably happen 100% because the larvae can actually continue on. There are ways to filter and clean that, and it has to be an automatic filter that will continually clean and manage those. And we do have product that works in that application.
Um, yeah, I mean, if you have any kind of details on how to manage that, feel free to talk about those. Yeah, we've got some time. That's all right.
Sure. So there's two different products that I think we use, and again, this is a little more in depth than probably we have a lot of time for because there's a lot of different factors that come into that. It's not just the zebra mussels; it's how they, what kind of flow you're trying to push through the system, what kind of pressure you're trying to keep in the system. We have products that we've done where we're running 3 and 4 and 5-inch systems that manage the zebra mussels, and those ones run on a Filtamat product. And again, giving you that information also comes back to those 4 questions that I asked right before this slide here. It's really, in order to give you the real consideration of what's going to work best for zebra mussels in your project, we need to know these 4 things in order to really give a good answer. But we have used Filtamat, we have used SAF filters in order to be able to manage the zebra mussels.
Great. Yeah, I think we're good to keep on going.
Okay, so we'll move forward.
Yeah.
Great. All right, so moving on with filters. Thank you for the questions, by the way. Great questions. Appreciate them. Don't hesitate to ask more questions at the end of this presentation. We'd love to give you the answers. And if we don't answer them now, we'll have my contact information at the end and we'll put together, you can email me and we can talk more about your specific questions. So water quality influence and the type of filter. What influences what filter we use and why? This is a tool called the hydrocyclone tester. Basically, this tool will allow us to determine how many parts per million of solids you have within your water. So this is something also that we would use to help determine what kind of filter we want to put into your project. Usually we do this test on larger sites. Smaller sites we kind of determine based on what we're seeing in the water. So as I mentioned earlier, there's a few different types of filters that we have and that are out there that we can use. There's manual filters. As I mentioned, a manual filter is a great application for something that's fairly clean water and that we're trying to get a little bit more precise on cleaning or for more of a micro system. The pros are, it's a simple installation and maintenance. Some manufacturers offer high quality 316L stainless steel, which is important. Typically propylene housing for corrosion resistance. It's a low cost. The common sizes you'll see are 3/4 inch to 3 inch. The cons, it's time consuming to manually clean. So you have to actually take it apart, clean the filter out, put it back together, and you have to have the system shut down. So there's a downtime, and it requires constant supervision. Semi-automatic filters. Again, it's got pros and cons. So it's a moderately cost option. It's simple installation and maintenance. Some manufacturers offer the high quality 316L stainless steel. The propylene or steel housing, so you can get them in both depending upon pressure and what your applications are. The typical sizes on these are 2 inch all the way up to 8 inch. It has a clogging indicator, so it will tell you when it's backed up and needs to be cleaned. The great thing about semi-automatics is that it can be cleaned without interrupting the irrigation cycle. And it also requires a low pressure in order to have a proper cleaning. The cons, it requires constant supervision. It requires a presence of an operator to perform the cleaning. So again, there's a maintenance cost to it. And now we talk a little bit about the automatic filters. So the pros are, it can be cleaned without interrupting irrigation. And again, manufacturers offer a 316L stainless steel screen. It's got a propylene or steel housing. Typically the sizes are 2 inch to 20 inch. It's fully automated and an optimized cleaning process, so it does it all by itself. It's consistent performance of the irrigation systems, keeping it managed and cleaning it all the time, make sure the system is running and operating at full capacity. And some manufacturers offer electronic and or wireless control with added HMI features. The flexibility of installation with these are great. Some of the cons is the product require a little bit higher pressure in the minimum pressure in order to sustain a cleaning cycle. Some of the products require a long flushing cycle with significant rejected water. So there is loss of water when it's cleaning. and it is a little bit higher of a cost. Couple videos here that I want to show you of self-cleaning and how they work. And I'll probably talk through them as we do it because it'll give you a little bit better understanding. This is a basic filter. The dotted line is your screen. When we open the valve to allow it to flow, as you can see, it's allowing the particulates to get screened or caught. And you know, we generally see apple cores in irrigation systems. Caught and hung up there, which allows your system to work. But if you watch it, the pressure is great. And watch that top right corner. As the system gets clogged, the pressure on the outlet side is now different than the inlet side. And when it reaches that point, that's when we know the system is needing to be cleaned. In this video, this will give us the relationship to what a backflush system would look like. Whoop, jumped the video, sorry. So we have the apple core and everything on there, and this is a focused back flush. We turned on the back release valve and flushed it back. And as you can see, it didn't clean the entire filter, it just cleaned a section of the filter. So it's just a back flush, not a focused back flush. Here we will see how a focused back flush works. You watch that cylinder on the bottom, notice the system is not interrupted. And of course it got rid of the apple core, which is good. So the system continues to flow, but it's allowing the focused back flush to fully clean that filter in all the way through. All right, so now we're going to talk a little bit more about what is the best filter for my application. Manual filters you want to use when water quality does not clog the screen in a very short time. I know that's very simple, but if you think about this, generally the water quality would be clean or somewhat clean and only have some particulates coming through that we're catching in the size that we want. If you have a worker or if you have to go out and clean that filter more frequent than weekly or monthly or whatever your time dictates, then it's time to consider going up to a semi-automatic filter. Now, a semi-automatic filter, if you're using it, will still require you to check it, but it will have an indicator that gives you a little trigger that tells you that needs to be cleaned. And if you're continually cleaning that, you would want to consider moving to a to a fully automatic filter. This is all relative to going back to Micron, the size of Micron. On average in the landscape, we're going to use 130 to 200 micron. And when we're flowing in that range, we want to consider how much particulate's going to build up on that screen before we have to clean it. And if it's a manual filter, again, we're going to have to clean that quite frequently if our screen size is 130 and our particulates going through there are in the range of 200 micron and in that case, you would consider going to a little bit more of a semi-automatic filter or a fully automatic filter to give yourself a little bit more ability to have flexibility with your system and keep it at operation. And the way that they determine that in the semi-automatics and automatics that have indicators is by pressure differential. So when you have 100 psi coming in and 100 psi going out, as that filter gets clogged up, you may have 100 psi coming in and 98 going out. We determine that factor at 7 psi. When there's a differential between the inlet and the outlet of 7 psi, that gives you an indication that that filter needs to be cleaned. So on the semi-automatic, your indicator will go up and tell you to clean it. On the fully automatic, it will automatically clean it. On the manual filters, you're kind of guessing. That's why we want to use a little bit better quality of water for the manual filters in order to manage that system. So we have a few examples, and I'll go through these to kind of give you an idea of what we've done and the projects that we've done out there. And then we'll jump into some questions. This is the U.S. National Whitewater Center. It's located in Charlotte, North Carolina. It's the largest whitewater park in the world. The National Olympic Team training site for USA canoe and kayaking teams. It utilizes 12 million gallons of water and can move 536,000 gallons per minute. So again, going back to our flow rate, that's pretty high flow. The water source is a swimming lake. Our operating conditions on this are 9,500 gallons per minute. And if you look at that big manifold of filters right there, those are self-cleaning disc filters, and they're at 130 micron and removes particles, offering consistent water quality over the entire open season. So it was a great project and a great application for filters. Not so much as the landscape, but it gives us the idea. This is a city sports complex located in Centerville City, Utah. And the application is a landscape irrigation for a city park. The water quality was good to average. It was a pressurized irrigation water. It's operating at 400 gallons per minute, and it's an 80 PSI system. The solution, we went to an automatic self-cleaning screen filter with a 200 micron screen, and it significantly improved the water quality, removing sand and debris, minimizing human intervention, which allowed them to do their other maintenance projects instead of cleaning nozzles and sprinkler heads all day. This is a Lehigh City Parks, Lehigh, Utah. The application here is a landscape irrigation for a city park, another one. It's just a different format of the way this one was installed in a different product. The water source is quality. It's a surface water, pressurized irrigation from canals. It's average. It's 100 GPM, 100 PSI. In this solution, we went with an automatic self-cleaning filter. It's a 200 micron, and it was installed to replace a semi-automatic filter because, again, they were cleaning it too frequently, and they said, we need to go to an automatic filter so that we can keep our maintenance on different things and save money. And it drastically reduced the human intervention. Canyon School District, another application for landscape on a junior high school. This water quality was, again, a surface pressurized irrigation. It's good to average, 270 gallons per minute, and it's a 90 PSI. And again, they went with an automatic self-cleaning screen filter at a 300 micron. It proved to be effective, removing the large debris and particles present in the water source, allowing them to use a secondary water source, reducing their operating costs. So they were allowed to take from being on a culinary water to a secondary water source, allowing them to save some money and water resources. Again, another Lehigh City sports field. This one was good to average water source. It's 200 micron. It's a great, again, putting them on a secondary water source and helping them to be able to decrease their water use of culinary water or treated water, which is what we use in our homes. So just to, go back and kind of give a little bit of recap on a few things. Each application is different. Every site's going to be a little different. There are some generalizations that you can use in terms of pressure and flow and those things to consider when you're putting together the applications in your project. But If you are dealing with a commercial site that is going to only be maintained once weekly or something like that, and the water quality is average to low, your consideration for a semi-automatic or fully automatic filter is probably going to be something you want to lean towards, just for you, ease of use and peace of mind that you're not going to have issues with clogging of nozzles and emission devices on the back end. But wanted to thank you guys for the time, and Damien will jump in and we'll answer some questions.
Yeah, so I think it's a good point to clarify because I think in a lot of design instances, a mentality of one size or type fits a specific application, over others is a common mentality. But I think the thing to clarify here is that that is not necessarily the case. That you've got so many different factors playing into what kind of filter is really best for your application or your project. Um, Less of a question and more of a statement, really, or a confirmation. But I think from a question standpoint, it's more of a practicality question. But how easy is it to actually, replace one type of filter, with another, whether it be going from manual to semi-automatic or semi-automatic to fully automatic? How easy is that
Mhm.
in most cases?
That's a great question. Most, depending upon the line size, if you're running at a 2-inch and you're replacing from a semi to a fully, you can typically replace without too much issue. You might have to put a few elbows or something in here and there, and depending upon how the original installation was put in. But we offer tons of different options and configurations to help enable you to be able to do that type of setup if you need to.
Yeah, great. Got a two-part question here. Does a focused backflush come in semi-automatic and automatic? And the second part to that, is a scanaway considered a focused backflush?
Yes and yes. So semi-automatics come in either a brush away or a scan away, which is basically the same thing as a focused backflush. And then the fully automatics are typically a scan away type of product, which is the focused backflush. So yes to both answers, or to both questions.
Cool. Yeah, nice and easy.
Mhm.
Um, how do you install filter systems in freezing conditions?
That's a very good question. So in freezing conditions, depending upon where you're located, for example, where I'm at in Southern California, we actually freeze in my location. So, but we operate our systems year round, so we can't really shut those down. So with that type of application, I would highly recommend or consider using a polar blanket or I shouldn't say polar, a barrier to cover the filter to protect it during those freezing conditions. If you are in a freezing location where you totally shut the system down, it's recommended that we have an entire YouTube video on how to properly prepare for winterization. And I would still even recommend to put a blanket or something on it as well to protect it.
Do certain manufactured enclosures, play a part in that as opposed to, I guess, blanketing it?
Yes and no. The enclosures won't typically protect against a hard frost, but they will protect against a frost like what we might see in my region. Um, so even with an enclosure, and there are enclosures that are designed specifically for these different types of our product that we have, I would still recommend in freezing conditions having a blanket or something to protect it, especially if you go into a propylene type of housing. I would recommend going with that just to be safe.
Yeah, great. And just I guess a follow up to the winterizing a system. Does blowing out or winterizing the system actually hurt the filters at all?
So we don't recommend blowing them out. We actually have a specific way of winterizing them that there's a few extra little tubes and things that you remove and take off and ensure that, because when freezing, water doesn't blow apart the system if it has a place to expand to. So we recommend allowing the to be able to expand to certain locations to be able to winterize it. And so we don't recommend taking and connecting your compressor to it like you would on the rest of the system. And that's why we usually recommend to install that prior to your blowout so that you're not damaging the system, but then be able to winterize it properly according to that. And again, we have a YouTube montage on that kind of gives you a little bit more information that we have.
Okay, yeah, great. There was a another sort of follow-up question to the initial freeze question there was, and might take a little bit of backtracking, but the question was, do you mean to flush out the system during winter with a drain valve?
Hmm. Yes, somewhat. There are specific tubes that are, if you notice on some of the product, there's specific tubes that are running as your inlet pressure and outlet pressure. Those are typically the lines that would have more freezing capabilities than anywhere else. The casing, the housing, and stuff like that are usually, by draining them with such a drain valve, that typically takes care of that issue. Um, but the tubes and things like that would be more of a concern. So you'd want to make sure those are basically the ones you'd take off and undo, and allowing them to open up and allow the water to expand when it freezes.
Great. I've actually got a couple of questions. One that kind of I think might be answered by a slide previous that we've
Mm-hmm.
had. What do you consider quote unquote good clean water compared to average?
Very good question. I can,
So I think we could, backtrack to one of
I
the, I
can,
think it was the tables that kind of
yeah,
showed.
I can jump back to the water sources and share that. Oh, there we, well, this will give you a little bit of an, so the question was, what do we consider
Good quality
good?
water compared to average, and I think it's that
Yeah,
the top two of that second
this will give
second
you a
table.
basic idea. Again, this is very general and very vague. Every area and every location is different. Um, for example, our well water in Southern California is actually pretty clean and clear, other than a little bit of sand particulates in it. Whereas if you're in another location where they're going to be pulling from, and again, that well water, as it gets down to the bottom where it's running out, it's going to be dirtier because it's going to be pulling and sucking more debris into the pump. So every application is going to be a little different in terms of what's considered good and very poor or average. But I would, just to give you some ideas, I mean, if you're in the 5 parts per million, you're in the average. If you're, or below, if you are in the 5 parts per million and above, you're probably in the poor. And then the very poor is a 10 part per million. Um, and I know that's very vague and it's hard to understand what parts per million means when it relates to the actual water quality. Uh, but that's why we typically, if we have a system we're concerned about or a system you're unsure about, we can come out and test and make sure that that is accurate and what we want, so that we know which kind of filter we want to put in that system. I, in my opinion, would always err on the side of caution. So if I know my water quality is is good. Like most of my projects I deal with, or my home is on municipal, I know it's pretty good water, so I'm clear to go with that. But if I'm in the average, I err on the side of caution and put in a little bit better filtration device just to be sure that I know my system is going to be okay. I hope that answers the question.
Yeah, I think it does. It like you said, it's a hard thing to answer directly
Hmm.
without the, I guess, on-site information
Correct.
specific. But yeah, no, that was good. Thank you. So a little bit more of a specific question here. How do you determine what kind of filter to use for MP rotator and drip?
So again, this will depend upon your flow rate, your GPM, your pressure that's coming into your system, your dynamic and static, and then your water source. If you're asking what size of micron to consider for filtering MP rotators or drip, I would lean towards 130 micron to a 200 micron. In that range, puts you, for example, a 200 micron is equal to an 80 mesh. I would probably lean towards 130 micron for our efficient, for MP rotators, which is what I typically install on MP rotators or drip.
Yeah, great. And what type of power is needed for monitoring and backflushing? Low voltage or line voltage, or both?
So that's a great question. The different types of filters and different manufacturers will have totally different types of controllers, as you call it. Uh, Many of our product that we put out there is going to be fully self-contained with a battery operated controller. So no, not necessary to have a line voltage. It runs off of 4 AA batteries. If you have a larger system and you want to have it on a line voltage, you can have a controller that will run on single phase, double phase, triple phase, 120, 240, any of the different voltages you'll see out there. So really, it depends on your application and what you have available and what your tolerances are for maybe replacing batteries once a year. So I would consider, that, I hope that helps, gives you a range. There's all the different filters have tons. Now, semi-automatic are completely self-contained, and there is no electronics needed. When you get to the automatic, you have to have a controller that operates your flushing mechanism. And that is, again, battery or line voltage, either one, depending upon what your site dictates.
Perfect. Yeah, that was a really good answer. How, and this can be referenced, I think,
Mm-hmm.
on another one of the slides, but how much or how many mesh is 130 micron? We did have that
Yeah,
table, I think it was a little earlier on.
yeah, it was. Let me see if I can, here we are. So 130 micron is probably about 120 roughly.
I think you just dropped out there for a second, Ron. Can
Oh,
you go over that one again?
yeah, sure. Sorry. 130 micron is about 120 mesh. So that's where the table kind of meets itself, because as you can see, micron are go up as the hole gets bigger, and mesh goes down as the line measurements get bigger. So there's more space for clearance. So right at about 120 to 125, that's where they kind of almost meet each other in the same numerical. So if you were to do 130 micron, you'd probably be in 125 mesh or 120, 15 mesh, in that range. Sorry.
Okay, yeah, perfect. And how does cost compare? I know we kind of, um, I guess, went over this a little briefly, but cost compare with manual versus fully automatic. There's
Hmm.
obviously going to be, I think, a pretty significant difference just with technology. The addition of controller in
Hmm.
the fully automatic side, but even just ballparking, a standard size, I think, might be
Yeah,
useful.
most fully automatics don't go down below a size of a 2 inch. So when you're talking going to a fully automated, you really are going to be in a 2 inch line size. You can go down to an inch and a half and then upsize for the filter, but you also have to keep in mind we have to have a minimum GPM and a minimum pressure in order to have the fully automatic system. A manual 2 inch, you're probably going to be 2 to 2.5 times the cost to go to a fully automatic in a 2 inch range.
Yeah, I no, unless there was kind of a specific instance or a specific size, I think that kind of answers that question pretty well. I might have actually been expecting a little bit more, to be honest, but
Okay.
no, that's good. Um, so I think that actually answers all of our questions that we had in the queue. So. Uh, Guys, if you do end up having further questions or want to discuss any of this content more with Ron or Amiad, you can contact them directly. Ron did have some contact info on the final slide, which he's going to now. So just take note of that. I'll give you a minute to do so. Take note of that, and you can reach out to him or Amiad after this presentation. There is a little quick follow up here, Ron. What's the company phone number?
Oh, that's a good question. I'd have to look up corporate. It's on our website. I know that. I don't know if I have corporate. I can give you my phone number.
Yeah, I think that would be
Okay.
fine. Yeah.
My phone number is 951 202 0060. And my email is just ron.krause@amiad.com. And feel free to email me and I'll answer further questions if you have them.
Yeah. So thanks again very much, guys, for attending today. Again, under all the circumstances, we're very fortunate and happy to be continuing our webinar sessions for everyone, and are very happy that we're able to have people attending and continuing to learn new things. And just in finishing up, I want to say thanks to Ron and Amiad for his time in preparing and presenting with us, and hopefully it's been really helpful to those in attendance and anyone who watches this webinar back. Having said that, we are always posting our webinars up on the website later on today. So if you need to rewatch it or pass it on to anyone else who hasn't been able to make it to today's session, you can go to our website, our resources/videos page, and it will be up there, I think, later on this afternoon. But once again, thank you, Ron and Amiad, for jumping on board with us today.
Thank
I
you.
hope I hope everyone remains safe, healthy, and having a good weekend. Thank you.